All right, our next speaker is Bunney, and he's going to talk about thermal unbounded Unruh-DeWitt detectors in circular motion from the University of Nottingham. Cameron, whenever you want, the floor is yours.
Thank you. As Eduardo just said, I'll be talking about thermal unbounded Unruh-DeWitt detectors in circular motion. So in order to address this topic, I'll first talk about the greater research context and make some historical remarks. Then I'll follow up by talking about what the actual detectors that we'll be modeling, how they look like mathematically, as for thermal unbounded, they look slightly different. Then I'll talk about what happens when we bound our detectors, what happens when we add in some ambient thermal background, and then at the end, I'll discuss what's happening after all this and where the calculation should go next. So this is all grounded in a 1981 paper called Experimental Black Hole Evaporation. And in this, by Bill Unruh, and this was shown that you could have an analog effective black hole that was called a dumb hole with a fluid system and sound waves on top. And then this, because it was in systems that were inviscid, people then suggested that this could be in a superfluid helium or BEC, boson-ion condensate system. And so there were experimental proposals, and since the Unruh effect requires an accelerated system, considering something in uniform circular motion gives, in fact, a constant acceleration. And in an experimental context, this makes more sense than a linearly accelerated observer, since it allows us to keep a very bounded system rather than having a very, very long lab. And so the basis for all this was laid out in a 2020 paper that had a look at the temperatures one might measure for both a relativistic system, and then also it was transferred into a non-relativistic lab-based system, and the response functions and temperatures in both 3+1 and 2+1 dimensions were laid out, and that was in a paper by Biermann et al. So the main detector we consider in a 2+1 Minkowski space, and it's in uniform circular motion. The radius is capital R. It has a angular velocity, capital omega, which we say is positive. And then what we probe is some massless scalar field phi that is in initially in a vacuum state. The variables I use are lab frame energy, E bar, and lab frame time, because I'm doing this non-relativistically. We have two possible interaction Hamiltonians. They look effectively the same. So chi is some switching function that allows us to turn on and off our interaction. C is the coupling constant. Mu is the monopole moment operator of our detector, and then phi is our field. So the second interaction Hamiltonian has a derivative in, and this is for technical reasons in the thermal case, because if we don't include this derivative, we actually induce in the Biermann function an infrared divergence. So this dt actually cancels this out for us. So if we use first order perturbation theory and calculate a transition probability for our detector to go from some ground state to an excited state, we actually split into one part is entirely due to the setup of the detector, this prefactor, and then this f chi is our transition, is our response function, which is the thing we're interested in. There are two forms. The top form is for a zero temperature, and then the bottom that involves a thermal expectation value is for our thermal system. And we'll use some inverse temperature beta. And then this is just the usual transition response function form. So then some limitations. We require, if we look at something on a stationary trajectory, then in fact the Biermann function is not a function of two variables, but it's actually only a function of the difference in the 2 times of the so we have the Weinmann function is phi of x and phi of x prime. It's only a difference between the times that we need to consider. And fortunately, the derivative coupled thermal Weinmann function on a circular trajectory also shares this feature. And the main limitation is that we consider infinite interaction time. So we let this tend to infinity. And then since we have a function of only the difference in times, we can divide out by the total interaction time. And then we get what I will now refer to as the response function. That is effectively a Fourier transform of the Weinmann function. So now onto the cavity calculation. We can induce a cavity by enforcing Dirichlet boundary conditions at some radius a, and we have that the detector is at some radius less than a, and then we can call the velocity of the detector omega times r. This will be less than 1. This is our effective speed limit on the system. Since we're using natural units in a relativistic system, this would be that the detector travels slower than the speed of light. In an analog system, it's that our detector will travel slower than the speed of sound. Now, if we go through and calculate the integral from the previous page, we end up with a mode sum in terms of Bessel functions. So J are Bessel functions, and the QMN is the nth zero of the nth Bessel function. And how the detection works is that this delta function picks out each time that our detector will tick. So it's nice and quantized. And if we increase A, we can see that this 0, the QMN over A, gets smaller and smaller. So this forces our delta peaks to get closer and closer, which might give us an idea for a particularly interesting limit to consider. A technical point is that if we look at E bar greater than 0, due to the argument of the delta function, we actually require that a point co-rotating at the boundary needs a velocity faster than the speed of sound / the speed of light. So A omega is greater than 1. If we don't impose this when E bar is greater than 0, then the delta function will never have 0 argument, and so the detector will never tick. So this tells us about the size of the boundaries that we can actually use. However, if we look at E bar less than 0, there is no such restriction required. So how do we get any interesting limits? Well, because we have a delta function, the easiest way to remove this would be to integrate over all the possible ranges of energies. And so if we introduce some smooth function of compact support, sigma, and integrate over the energies, we can remove this delta function, and then this allows us to consider only certain energies. So from an experimental point of view, this would be pointing out the specific ranges of energy that we'll be considering. And if we do this and then take a limit in measure of A going to infinity, so the large boundary limit, we can actually get analytic results out. So what happens is the very first term that we see in this response function is the standard vacuum response function. But then at order 1 over A cubed, we get a response for E bar equal to plus or minus omega. So we get some sort of resonant effect picked up by the system whenever we look at energies that are equal to the angular velocity. And there's a cofactor alpha, which is given by this sum. Numerically, this turns out to be about minus 0.2, as far as I can find. There's no closed form of this sum. And this makes sense because when we're imposing a boundary, it makes sense that the number of modes that can actually be detected by the system are reduced. So this, the fact that alpha is negative is exactly this reduction in detectable modes. So this is the main interesting limit when we impose a boundary. However, if we
2 minutes.
Okay, thank you. So I'll quickly talk about the thermal case. The temperature associated with this. So we have the Einstein detailed balance condition, which allows us to define an energy-dependent temperature. And if we have E bar not equal to plus or minus omega, we get exactly the same as the vacuum response. However, if it is equal to plus or minus omega, this tells us that we should get an infinite temperature response. However, that perhaps suggests that when we have a delta peak spectrum, the concept of energy-dependent temperature is no longer the useful thing to consider. And even before we took this limit, the mode sum response function has the same issue. So very quickly, thermal detectors, so detectors that are in some ambient temperature of 1 over beta, immediately gives another mode sum response function, where the first term, so this 1 multiplied by the Bessel function, is the vacuum part, and then we have this Bose thermal factor multiplying by the Bessel functions that give us the thermal contribution. There's an overall E bar squared because this is from the derivative coupling, and in fact the vacuum term is divergent if we would consider this Machian or supersonic limit as we sonic limit of approaching the speed of sound. There are 2 interesting limits to consider, high temperature and low temperature, but I'm going to skip over those for now. They just have analytic forms that you can get via expansion under the sum, and we are able to do that via a dominated convergence theorem argument. So if we want to look to the future, and we apply both a background temperature and a boundary, we get a mode sum that is in terms of that mostly looks like the cavity calculation, except we now have this extra thermal part. And what we can do is we can change this sum slightly, where we use omega as either, as we saw here, the standard dispersion relation, the linear dispersion relation, or we can model a Bose-Einstein condensate by using a Bogoliubov dispersion relation. And I think I've pretty much run out of time now. So a last limitation would be finite time interaction, removing that and having a look at this. But that is for the future for now. So all I can say is thank you for listening.
Thank you very much, Cameron. Right in time. All right, we have room for 1 question, and Cisco even almost acausally put a hand up. Cisco, right.
Hello, thank you, and thank you, Cameron, for the talk. It's very nice to see these results come together. I was just wondering if you could, just in a quick way, give the take-home of the 2 limits for high and low temperatures for ambient background initial temperatures. What do we learn from those 2 limits? Is there a quick take-home that?
The main thing that we learn from them is that the limits make sense. So in the low temperature limit, the temperature is exponentially decaying away. So if we have very low temperature, it tells us that the temperature really shouldn't affect our system. However, in the high temperature limit, the temperature is linear, in fact. So it's not exponentially increasing, but it's only linearly increasing. So it tells us that both vacuum and the thermal contribution are both sort of important. So the vacuum is only at subleading importance, but it still should be taken into consideration, I think, would be the main 2 takeaways.
Okay, perfect. Thank you.
Okay.
All right. Thank you very much, Cisco and Cameron. Let's thank Cameron again for the talk.
Thank you.